start or?
Yeah, it's an
Okay.
audience.
I'll start writing and we'll see if they come down. So, thanks to the organizers of the seminar for inviting me to speak here. I'm giving what in some sense is a sort of talk I gave in a workshop in the other seminar room a few weeks ago, but I will make it self-contained, and so you don't need to remember what I said, whatever it is, a month ago. But I will recall the theorem that sort of motivates my interest in what I'm talking about today, which is the following. It says, we have gamma sitting in S1R, and should be bigger than or equal to 3. M compact manifold. The dimension of M less than n minus 1, and rho from gamma to diff M, then rho of gamma is finite. So this theorem proves a conjecture that Zimmer made in 1983. I've only stated it in a special case, but I just want to state something to motivate the interest of the question.
Gamma is lattice.
Oh, thank you. And in fact, even worse, gamma is cocompact lattice. If it was just a lattice, that would be good, but I want it to be cocompact for the point of this theorem.
I thought this was your theorem. Now these other guys have their names on it too.
This is my theorem with Aaron Brown and Sebastian Hurtado. Those are my collaborators.
Okay.
So I believe I mentioned their names in the other talk. I certainly hope I did. So there's a sort of key point, there's sort of the pivot point of this, the proof of this theorem, which is the following definition that I'm going to make in order to state another theorem. We'll call that one theorem 1. The definition says I have rho, and now it's really from any gamma at all you like to diff M, and let's just, gamma should be a finitely generated group, generated by some set S. Then this action has subexponential growth of derivatives if for every epsilon greater than 0, there's some constant c depending on epsilon, such that if I look at the norm of the derivative of rho applied to an element of gamma at a point x, it's going to be less than or equal to c times e to the epsilon times the length of gamma. Where this is why I specified that the group should be finitely generating, so I want to have a reasonable word metric on it with respect to which I can measure these things. And this should be true for all xing values. And this is the part of the talk that where I'll be a little vague. So there are 2 points in the proof of this theorem. One is to prove this property, and the other is to use this property to conclude. And I will say that what I'm doing today is telling you the second half of the proof. So that's what I'll do for the rest of today, is tell you how to use this, once you have this property for your action, how you conclude the proof of this theorem or many other theorems like it.
And then next week.
And then I don't know, if someone wants me to give it, oh wait, there's a workshop next week. I can explain the other half if people want. The reason I chose to do this half in this seminar today is that the other half is very much more dynamical, and this half is very much more sort of through theory and in the flavor of this semester. If people want, I'm happy to explain the other half in private or in a talk or in whatever venue people like, any time between now and the end of this week.
Which half makes use of cocompactness?
What?
Which half makes use of cocompactness?
Currently both, but, well, let's put it this way. When the theorem was proved in 2016, both halves did. And I'll say a little bit more about why the second half doesn't as I go on. It turns out that both halves did, but the second half actually does much less. So the second theorem, which I'll have to make a definition to make clear what it means. So it says that if gamma has something that we will call strong property T of Lafforgue. I'll be dropping the of Lafforgue very soon, and rho from gamma to diff m has subexponential growth of derivatives then rho of gamma preserves a, I'm just going to claim smooth Riemannian metric. And for the purposes of this talk, if you like these kinds of decorations, I can put an infinity there. We actually have a theorem with much less regularity, but I'm assuming that's not the direction of technicalities in which this audience is most interested. I gave this talk in front of a dynamics audience in Stockholm last week, and they really care about what number you put here very deeply. So now you know the point is that there's another theorem which will contribute variously to Lafforgue, de La Salle, and de La Salle de Watt. It says if G is a higher rank simple Lie group, and gamma in G is a lattice, then gamma has strong property T. And again, this really depends on what moment in history you actually believe you're in. I should be saying here co-compact, if you want things that are extant in the literature. Brown, Hurtado, and I were thinking about how to remove this, and it turns out that de La Salle beat us there. It turns out really, people had thought this was a hard question. I mean, I had a conversation with Asaf Noor at Princeton in December where we were both agreeing that removing the co-compact was a very difficult question, and we turn out to have been wrong. You have to be careful in various places with an argument that is very delicate, but it turns out the existing argument plus a few observations allows you to get past this point. So this is actually now going to be another theorem of de La Salle's that works in general. I mean, there's some work there and there's some clever observations. Brown and Hurtado and I had made 2 of the 3 you need, and he made all 3, so he beat us to the punch. But it really is now more or less known for all cases, and it's much less difficult than I expected. I expected it to be, in December I thought it would be impossible. And I can say more about that later for people who want. So now, I've stated 2 theorems without giving you a definition of the word. So the next part of the talk is what is strong property T. Because I wasn't sure exactly of my audience, I will first remind you what is property T, because it is a strengthening of property T. So, how do I want to do this? My definition is gamma has property T of Kaizen. If for every unitary representation of gamma with no invariant vectors, just to make life simpler. If I look at how much I move some vector by an element of gamma, and they take the supremum, really, when I say supremum, the maximum over my finite generating set, this should be bigger than epsilon times the norm t. So, this is Kazdan's, more or less Kazdan's original definition. He said this in terms of the felt topology, but it turns out to be more or less mean this sort of immediately. And so this is what it means to have property T, and now we want to strengthen this somehow. And I did not use the words correctly. So how do we want to strengthen this? There's a definition that I like to make that says, well, if I have I from gamma, there are lots of games people play, varying this property, strengthening this property, proving equivalent properties. I'm not going to get into all of that. I will get into a little bit of it. What we want to look at is a representation just by bounded operators instead of by unitary operators. The reason why might already be clear based on this equation. That's not unitary, that's some sort of growth condition. So what we'll say is this has epsilon subexponential norm growth. If when I look at the norm of pi of gamma, that should be less than or equal to, if, so I want there to be some constant, that should be less than or equal to my constant times e to the sine of gamma. So my elements aren't unitary, but their norms are growing slowly. And the thing to keep in mind here is the norms aren't growing that slowly, because the C you should think of as being a tremendous number. So their norms are growing eventually slowly. And that's the same thing that's happening there, is eventual slow growth. Immediately, the norms might be 10 billion. They're very, very non-unitary. But eventually they grow more slowly. And maybe, I'll wait till after I make a definition to say those things. So there's a problem with this property in this definition, which is that you could have this property with these kinds of representations where what I was doing to my vectors, instead of moving them around, right? In a unitary representation, if I take a unit vector, it swings around on the unit sphere, and this is saying it swings at least a little bit. In this setting, if I try to make this definition, my vector might be almost invariant just because it just gets a little bit bigger under every single one of my generators. And property T is somehow about finding fixed points, about finding contraction in a way that I'll make precise soon. And if all I had was the condition that each one of my vectors got a little bit bigger, my vector got a little bit bigger under all my generators, you might then think that, as I multiply by more elements and did bigger words, my vector would just grow under the iterates of this representation. Because after all, this slow norm growth condition just says vectors grow slowly. And so, this is a very bad definition from the point of view of these kinds of representations. And I think one of Lafforgue's central insights in this game is giving the right definition. And so to do that, I just want to make a few definitions. So there's an operator many people who like property T like, which is the operator that, we look at this measure, which is the measure that's equidistributed on the generator.
So you didn't tell us what strong property T is?
I will in a second. I'm going to tell you the different definition of property. I'm going to tell you the different definition of property T, and then I will directly generalize that one.
But somehow you're saying, you are telling us that this is going to be the right expansion of the notion of unitary to define.
Yes, this is the right expansion of unitary. You want epsilon sub-exponential norm growth for small values of epsilon. That's the right sort of context to be in for strong property T.
So
because
you
it's
told us
just
that
above
that's
the-
not the right definition for generalize.
Yeah, that's not the right definition to generalize. Yes, but somehow I thought pedagogical to mention it. Maybe I was wrong.
As a first approximation, you can assume that it's all bounded.
Right, you could even assume that all the operators are bounded. That's much less useful.
But it's
Better than all the representations are unitary, and this is still not a great definition. Even if all the elements are bounded. But this turns out to be the right context, both for our application and for the application Lafforgue originally had in mind. So maybe everyone in the room knows this, but I can use this to define an operator where I take a vector and I average it over this measure. can do this also, this definition doesn't really depend on choosing that measure. I can do this definition for any measure, and I will be doing it for other measures in not very long. And if I have pi from gamma into unitary representations of h, there's also a nice thing that we have, which is that h splits as the invariant vectors plus an orthogonal complement, which is also invariant, right? This is just a property of unitary representations that's very easy. And so I can also define a projection P from H to H invariant, and this is an orthogonal projection. And this behaves very nicely in the context of this, this projection commutes with the action of gamma in this context. And so, there's a proposition. That says that gamma has property T. This happens I'm just going to do the forward implication. There is a reverse implication, but I have to set things up slightly more carefully. So it says that if I average over mu, I take this averaging operator and I subtract off the projection to invariance, that should be strictly less than norm v, which is the same thing as saying that this pi mu operator restricted to the perpendicular to the invariance has norm less than 1, which is the same thing as saying there exists some constant less than 1, such that pi of mu star to the n v minus projection on invariance of v is less than c to the n in v. All of this is just rephrasing the same condition. And it's very easy to prove the proposition from the definition, just because what am I doing? I'm taking my vector, I'm looking at its projection to the complement to the invariance. Now I know it moves around, and it's just convexity of the Hilbert sphere that means that as I average, it drops in. So this is a very easy fact. It is, I'll say that it's, in some sense, it's the most useful form, I think, of property T. Certainly for dynamical applications, where Lewis and I had great fun with this about 10 years ago. This was the definition we needed to do with many things. And I think really, from some honest point of view, it's also the most useful definition for many other things. And if you want to know not just that expander graphs exist, but you want to know the expander mixing on it, you want to know that random walk on an expander graph mixes exponentially fast, this is the definition you're using.
So this is equivalent, or you wrote one?
I always get a little confused about this, and I made a mistake in a talk I gave in Evanston a few weeks ago. If you pick the wrong generating set for certain groups, you can have this for other groups. So if you say for all generating sets, then it's equivalent. You have to be a little careful about a few things, and it really is just if you pick the wrong generating set for some group of isometries of the Euclidean space and look at the wrong maybe it's okay once I say for all representations, but there's some tricks involving groups generated by reflections where you occasionally get this property when you wouldn't expect it. So it has to be a little more careful than I'm capable of being on my feet. What? It should be equivalent? Maybe it's equivalent. There's some mistake I made with it when I gave a talk in Evanston, and therefore I don't want to make the same mistake, so I'm avoiding it. If it's not equivalent, it's equivalent up to observing some minor modification of it.
Group is finitely generated, it's equivalent, but not for topological groups, I guess.
Yes, I mean, you can take it to be equivalent and you won't be very far wrong. So now that we have that proposition, that we can put the reverse arrow on, except I'm not going to move the board just to do that. We can make Lafforgue's definition which I have sort of approached slowly. I've approached slowly because if you just see this definition, you just are overwhelmed by quantifiers. And I think it's, I'll make some more comments on that in a minute. So gamma has strong property T, but this is actually not Lafforgue's definition, in some sense. If there exists some epsilon naught and some measures mu n supported, these are probability measures on gamma with the support of mu n lying in the ball of radius n about the identity, such that for all epsilon less than epsilon naught and all pi from gamma to bounded operators on some Hilbert space with epsilon subexponential norm growth,
You just need S to be symmetric.
yes, you need S to be symmetric. You're right. That's right. If S is symmetric, that fixes it. Yeah, thank you.
You need pi of mu to be separate.
Yeah. If S is not symmetric, then it's not equivalent. But if S is symmetric, it is equivalent. It's good to have smart people in the audience. What I'll say it informally first. It says that pi of mu n converge exponentially quickly to a projection on the invariant vectors. And one should actually say this correctly, i.e. there exists lambda less than 1 and p from each to each invariant such that something that looks very much like what I just wrote. There's also some constant c greater than 0, such that pi of mu n v minus p of v plus the ratio of some constant. So it says, the upshot is that still have fast convergence of averages to invariant vectors. And now there are many things about this definition that are messier than you'd like them to be, some of which have been fixed. And so, if you read Lafforgue's paper, I had this very funny conversation with Malone Lindenstrauss when he was visiting me in Bloomington. I gave him this definition more or less verbally on the way to lunch one day, and Malone swallows quantifiers easily, so he swallowed as many quantifiers on the walk to lunch, and then without really any problems. And then he went and looked at Lafforgue's paper and he said, but that's not the definition he wrote down. He writes down this thing about some algebra of functions and some projection. And I said, yeah, it's the same thing. I've just translated it for you into non-operator algebra language. And he didn't believe me at first, but eventually did. So this is not Lafforgue's definition. This definition is, in various parts, this definition was given by De La Salle and De La Salle as they were working on generalizing Lafforgue's property. One of the things you can do that I'm not going to bother with here is you can change H to other Banach spaces. And this is part of the interest in the property, is that it does generalize the proof of the property, and the proof of property T is somehow very much likes Hilbert spaces, or at least likes nice Banach spaces. The proof of this thing is more flexible. And so it likes a wider class of Banach spaces, and this is one of the interests elsewhere in the property. This is not my interest in the property today, even though we do use it in the paper. We use it to get, when I said I put an infinity and that I could put smaller numbers than infinity there, if you want to get smaller numbers than infinity there, you have to start worrying about other Banach spaces. But that all becomes quite technical, and life is easier if you just think about Hilbert spaces. And the other thing that isn't stated in any paper clearly until ours is this exponential rate of contraction. The proofs all prove it, but they don't say it in the definitions or statements of theorems.
So it's a projection.
What? It's very important that this is a projection, because orthogonal projection is not a nice thing. And so you just get a projection. I mean, really what you get is this sequence of operators has a limit in some operator algebra, or in some space of operators, and that the image of that limiting operator maps the whole space onto invariant vectors. And they're you know, I guess Cornelia and Piotr Novak have a paper on this, and this De La Salle has a paper on this, that you might wonder, you know, can this projection be taken to commute with the group action, for instance? Not always. There are various small technicalities here that you have to, you know, there are lots of things that, in the context of property T, you can play games. I'll assume this, and then it implies this stronger thing, and then this, and that, the other thing. And most of those games don't quite work in this context. One thing that De La Salle did prove, but you have to read his proofs and not just the statements in his papers. I keep writing this sequence of measures as mu sub n, rather than mu convolved to the n. You can pick some measure for which it's mu convolved to the n. You can't pick the equidistributed measure on generators, at least we don't know that you can, and say mu convolved to the n. Mikhail says he doesn't think you can. All I'm willing to say is I don't see any way conceivably to prove that the convolution powers of that work.
So Bn, so this is Bn of gamma. This is the support. It's supported on both the Cayley ball.
Yeah, the Cayley ball. You somehow want, you know, you don't want to have to be using big elements. So it's some sequence of measures that look more or less like the convolution powers of the generating measure, but the exactness distribution on the Cayley ball might be different.
Is P required to be the identity on the invariant vectors?
What?
Is P required to be a projection in the sense that it restricts to
Yes, it's a projection in the sense that P squared is the
P squared?
But I actually thought that since this, I mean, you can apply this to the dual, I thought you really get the orthogonal projection. I mean, at least in the Lafforgue.
You get the orthogonal projection if you're in the unitaries. I don't think you get it in general for bounded operators. I mean, I could be wrong, but I don't think you get it in general if you're just bounded operators.
Because, I mean, his definition, okay, we can discuss about, in his definition he requires the existence of an idempotent, both for the representation and for the dual representation. And because of this, you actually get that that must be the projection.
Right,
But maybe
right,
this
but
is slightly
I've hedged and shaved this definition in ways where maybe I'm not assuming as much as he was assuming, and so because there really is, there's a paragraph about this long in our paper where I attempt to explain the evolution of the definitions. So definitions definitely are undergoing, you know, this property was defined in 2007, so relatively recently. It's a relatively complicated property, and so there's still some, you know, I don't know that we know, you know, with property T, we know the correct definition. In fact, we know like 12 correct definitions, all of which are equivalent. We're not there yet with this property. Cornelia and Piotr Novak have a paper where they try and help us get there, and Mikhail De La Salle has a paper where he tries to get us there, but I don't think we're there yet by any stretch of the imagination. It's, you know, there are things left to be understood about this property, even at very basic levels. Like, you know, you really want that you can just average over the generators. It seems completely absurd that you can't do this, but you can't, you really can't prove it.
So does it mean, sorry?
Yeah. So I want to make a few more remarks about this property. One is that one of the first things Lafforgue proves about this property that works no matter which definition you're using is that no hyperbolic group has this property. So it immediately becomes a much less robust property than property T, where, you know, a generic group in various senses has property T. No groups have this property except higher rank lattices at the moment. So in some sense, I shouldn't have played down Mikhail's contribution with finishing the proof for non-uniform lattices, because he's vastly increased the collection of groups with this property. And the only other groups where it's even conceivable to me that you might have a proof of this, you know, these exotic, you have these exotic rank 2 buildings that have co-compact lattices. And there's some partial results by Isar Oppenheim that make you believe that maybe those groups have strong property T. Its partial results are very partial in this direction, but it's conceivable that those groups have this property. I'd be interesting to know another good candidate of a group to try and prove the property for.
The property is sometimes a fixed point property. This property you can formulate in terms of fixed point of something.
So the answer is it implies many fixed point properties, but you already have, once you move off of Hilbert space to more general Banach spaces, that the version of property T and the fixed point property are different, and the fixed point property is much stronger in general. This one has the opposite property, that it implies some fixed point properties, but it's still not clear that there's a good formulation of equivalence. It'd be very interesting to know if there was a right formulation of a fixed point property that was equivalent. Again, we don't currently know that. All right, so now I've told you what strong property T is and told you a few things about it. And now I just want to tell you how to use it. So next part of the talk. And so I will verbally tell you that there are. So Lafforgue invented it for the strangest of possible reasons, which is he invented it to obstruct certain proofs of the Baum-Cohn conjecture for strong property T. There's a standard way of proving the Baum-Cohn conjecture that's known as the dual Dirac method. You're sort of taking the proof of Bott periodicity and generalizing it 10,000-fold. And he wanted to show that you couldn't do that proof for higher rank lattices, which is a strange thing to be trying to show in the first place, that a proof can't be done. But he did really get, this is something I don't quite understand entirely. The amusing thing is, when he wrote this paper where he made the definition, that was clearly his motivation. And then he wrote another paper where he explained how you proved that, and he needed to wiggle the definition a little bit in a direction that's very different than this one. So he needs a slightly different definition of strong property T, where again, it's not clear they're equivalent. It is clear they have the same proof. And so that's what he started with. There are a few other applications. One is you can prove higher rank lattices don't act on hyperbolic space, some hyperbolic spaces this way, but there are now better proofs of that are much more general in the result and much softer in the technique. It is true that this allows you to prove certain fixed point properties for higher rank lattices on certain classes of Banach spaces that are much more general than you can prove any other way. The other thing that it is good for is, there's an interest in Banach space theory. The definition of expander graph for us is something about cuts in the graph. The definition of expander graph for these people is take a family of expander graphs. They have a family of graphs that embed poorly in Hilbert space, and you want to replace Hilbert space with lots more Banach spaces. So you can use variants of this property to build what are called universal expanders, where they don't embed nicely in any Banach space. And that was one of the original applications of this. But somehow that application is a little disappointing, because for that application you can go back to bounded operators. You just need fancier Banach spaces. Somehow
You need to go back to
unitaries,
yeah,
but more general Banach spaces. And the other thing is this: for this application to fixed points, they're really always looking at fixed points on isometric actions. And then you don't need this kind of epsilon subexponential norm growth. This is an exponential rate of norm growth. You really need a linear rate of norm growth for their proofs. So somehow every application that's had so far has used at most a fraction of its power, or been to prove that you can't prove something. So I like my application because it's the first application where you need the full strength of the property, and you're proving something, not proving that you can't prove something. So I'm going to tell you how I use it rather than how someone else uses it. So I'm just going to start with M, a compact manifold. We're going to get a little more geometric now, nice and theoretic. So I'm just going to be an arbitrary compact manifold, and I can look at Riemannian metrics. Y in the set of sections from M to S2 from, I should say, M star. These are A Riemannian metric at every point gives you these GIJs, which is the same thing as giving you a symmetric symmetric two-tensor. And where are the Riemannian metrics here? They're the positive cone in this vector space. And if gamma acts on M, then gamma acts on this section. And so this is where we're going to be looking for fixed points, rather for invariant vectors. We're going to be trying to apply this property in this action. And you can notice right away that I've been a little bit vague, and that I just say sections and I don't say anything about regularity. When if you're a Riemannian geometer, you always assume these things are at least smooth or at least C2 or something. And there's a problem with that, in that while this property applies to Banach spaces that are much more general than Hilbert spaces, it applies only to Banach spaces with some kind of convexity. And the CK norm on any space is sort of from the point of view of people doing pure Banach space theory, it's roughly as bad as the L infinity norm, because it has roughly as much convexity, right? Because it's a sup norm, like the L infinity norm, it has basically no convexity properties. So it's bad. So you could look at gamma act on L2 of M S2 Tm. Now, to be honest, I have to have picked a volume form to even define what I mean by L2. I mean, I could have picked some other measure other than a volume form, but I'm in this Riemannian context, so I might as well be picking a volume form instead of some arbitrary measure. And now I have an action on a Hilbert space. And you could look at this action and you say, oh, I'm going to use that property to find a fixed point in this Banach space. And regrettably, life gets a little harder than that. And it is true that let's name this proposition / exercise. And I'll do a harder version of the exercise for you in a minute, so you have to do it very fast if you want to do the exercise, which is that subexponential growth of derivatives implies subexponential growth, subexponential norm growth for the action that I get on L2 and S2 Tm star omega. Why is this? You can look at this and wonder, where is the derivative occurring at all? The derivative is occurring because I act on these tensors, right? I'm acting on two tensors. That action comes by the derivative, but that's the only place where you see the growth, except the volume form isn't invariant. And you worry about that for a while, and then you realize that subexponential growth of derivative means subexponential growth of Jacobians as well. I'll come back to that point in 2 minutes. But this is still no good, because
So even if you had a fixed point, how do you know that it's going to be a positive definite?
I'll get to that at the end. I will explain that. It's not actually hard, but it does use this funny equation. But here, even if I have a fixed point, there's something worse than that, which is I just have a fixed point in L2. It's not a very nice thing to have a fixed point in L2. You have an L2 metric, it's just terrible from all points of view. Yes?
Also acts on the cat-0 space of Riemannian metric.
Yes, and I have wanted to use that in our proof, and if you're using that instead of Lafforgue, if you're using that instead of this action, you can get away with less than Lafforgue's results, but you get less general conclusions.
How behaves the norm of?
What?
How behaves the norm of the same sort of operator?
How behaves the norm of this?
Acting on this cat-0 space.
On the cat-0 space, well, if you act on the cat-0 space, so first act on the cat-0 space of L2 metrics is with respect to metrics defining one volume form. And there you act isometrically. So there somehow you get much nicer, because any action by volume preserving diffeomorphism, if I assume the action preserves volume, then I act isometrically. And so you could use that action. This is what I thought we were going to do before we discovered this thing with Lafforgue's ideas. If you use that action and try and find fixed points there, which you can do, there's then some more work to do to get regularity, which is hard and has never been written, but I think I know how to do. You can work there, and it works very nicely, I think, except for the fact that you need an invariant volume form to start with, and here I don't want to assume one. There are other things you can do. We can talk about that more later if you like. But really what we want to do here is just look at, instead, we want to get regularity by looking at WPK as to Tm star omega. And by this I mean that the first k derivatives live in L2. This is the standard Sobolev space. And with the Sobolev embedding theorems, basically say in this setting that W2K S2 Tm star omega sits inside of C K minus dimension of M over 2 S2 Tm star. They say many more other things than this, but the point is if you find a fixed point in here where K is large enough, that thing still has derivatives. Because of the Sobolev embedding theorems. And in fact, if you could find a fixed point simultaneously in all of these guys, you'd have found a smooth metric that was invariant. And that turns out in this context to be no harder than finding one in the polar space. Now, to tell you why this all works, I need to tell you two semi-classical things, and then I can, in the end, address Emmanuel's question about why the invariant guy is not degenerate. So one needs the following semi-classical fact, which in dynamics runs under the title estimate on compositions, and this is used in some form in basically all of dynamical systems theory. But not in exactly the form I will state it in. In this form, this is first observed in the paper by myself and Willis. But really, it's not that original. So what it says is, if when I look at the derivative of rho of gamma at x, I have this kind of norm bound that I like, which is some constant times eta. Well, let's just say some other constant times length of gamma. So if I have that, then I have, well, I'm just going to make up notation. And I'm not going to tell you in very great level detail what I mean by the notation. I take k derivatives instead. And I look at the norm of this operator. And the hard part in writing this out is deciding what you want this to be. And giving a proof is deciding in what framework you want to define this thing, whether you want to work with jets or something, local coordinates or something else. You have to make a decision and you have to do a little bit of work. But it's not very hard work once you make a decision. This is going to be less than, well, C1 prime, e to the C2, k plus 1, L. So if C2 happens to be epsilon, then this is roughly, k times epsilon. And so, this says subexponential growth, upshot for us, subexponential growth of one derivative implies subexponential growth of all derivatives. And it really is the case that if you assume you're on a manifold that's, say, the torus, so you can work with global coordinates, or or on Rn, and you want to prove this, it's the chain rule. If you want to prove it for one diffeomorphism, for iterates of one diffeomorphism, you start computing with the chain rule and you'll see that this is true. Working on a general manifold and for general group action requires a little thought, but it really is, this is also known as the chain rule. And it is one of these funny things about doing this kind of work, which is people who do various forms of group theory and representation theory are interested in it, but there are all these things in the middle of it that turn out to be the chain rule. And if you go to talk in front of a dynamics audience, you never tell them anything about the parts that are the chain rule, because they all eat, breathe, live, and sleep the chain rule. You tell it to another audience, and they're like, that's really the chain rule? Thank you.
The chain rule involves, the chain rule involves differentiating the composition.
Yeah.
So what do you compose?
What am I composing? There's this length of gamma here, and so what I'm composing is generators to get words.
This is the second derivative, right? Or is it the
Maybe the kth derivative.
Yeah, okay, so how do you go from the first to the second derivative?
And you write down what the chain rule says for the second derivative.
Because second derivatives are not composed.
Right. When
So
you,
they introduce a term which does not expand.
right. Really the proof of this, if you write out the computation just for two derivatives on say R,
Yes.
which is
Right, it's a chain rule for
if you write for two derivatives on R, what you'll see is that the second derivatives are just adding linearly, and the first derivatives are growing exponentially. And the second derivative is growing exponentially, but only in terms of the first derivative. You just write down the computation on R. That's relatively easy to see. That what you get is your first derivative looks like something is looks like it's growing exponentially. Your second derivative under computation looks like it's growing exponentially in terms of the first derivative, but only linearly in terms of the second derivative. And it's just you really can see it if you do the chain rule for f to the third power. It'd be very visible. Maybe it's even visible in that. It's really the question of, this is an interesting thing. I don't know about in other countries, but in the United States, we never teach them. When we teach calculus, we teach everyone the chain rule. We never teach them the chain rule for the second derivative. Really, we should, but we never do. If it was something we all taught in calculus, we don't know it by now. The corollary of this is that, if I'm studying the group action, which has subexponential growth of derivatives, then the representation, we call it pi, of gamma on W2K m S2Tm omega has epsilon subexponential norm growth for all epsilon greater than 0. So in particular, I can hit Lafforgue's range of epsilons where x OK. I always forget to say this. Is epsilon 0 in the definition of a strong property T? Why do I phrase things with epsilon 0 and epsilon instead of just with one epsilon? The reason I do is because Lafforgue actually computes epsilon 0, and for SL3R and co-compact lattices in SL3R, the number is a sixth. It's not a mysterious number, it's a sixth. That's not useful to us today, but he actually computes a number. So what's the proof of this? The proof of this is just, estimates on compositions plus, as I said before, subexponential growth want to say one thing here for what may be the non-existent experts in the room, but I do want to say it, which is there's something very similar to this in a paper Margolis and I wrote 10 years ago, where he proved something very similar, assuming that the gamma action that doesn't have subexponential growth and derivatives, but is a perturbation of an isometric action. And we then use property T to find an invariant metric in a very similar way to what I'm describing here. That paper is much harder than what I'm doing right now, because what we need there, I've erased it. So in Lafforgue's definition of strong property T, there's always this big constant C that's allowed to be tremendous. And you're allowed to have slow growth of norms of operators eventually and not immediately. What Margolis and I have proved is that property T implies that if you have immediate slow growth of norms, then you still have all the properties you want. You still have, nice properties, but you need immediate growth. And then there's a lot of hard work to be done to do the computation I'm doing sloppily here to see that if I perturb an isometric action, the norms of the first iterates are very small, and it's only bigger iterates where they grow. And so there's somehow I feel like something dishonest in the way we've written the paper because we refer back to that one. To do this argument is much gentler. You're allowed to be completely sloppy because you can any sloppiness you make, you're only doing sort of finite computations. Any sloppiness you make, you absorb that into this big capital C constant, and you just don't care. So this is actually this part of the argument. This is not a dynamics audience, so people might think what I'm saying here has some difficulty hiding in it. I just want to be clear that it has absolutely none. This part of the argument is very soft. Now you know what happens. How do we end the game? So now we know that if I let Gn be pi of un of some g naught, I pick g naught a smooth Riemannian metric. We know that Gn converges to some, we'll call it G invariant, an invariant metric. And this happens in some W2K, so in C of some K prime, where K prime is K minus dimension over 2. But this happens for every K. And once you know you're in here, this convergence is pointwise. And so it doesn't depend on which one of these Ks you chose. And G invariant doesn't depend on K. So it's also C infinity. Now, small flourishes. And now the question is, why is G invariant degenerate? Question one asked me 20 minutes ago. And the point is, well, first thing you know is that G invariant of VV for any vector is at least greater than or equal to 0, right? Since G invariant is a limit of averages, so a limit of positive metrics. You're not worrying about suddenly getting a Lorentz metric in the limit. You're just worried about getting 0. And now what's the point is that Gn goes to G invariant exponentially quickly. This is this thing that I insisted on adding to Lafforgue's definition that I haven't used yet. But Gn of VV, which after all is just G0 of pi mu n v pi mu n v, shrinks subexponentially. So if you had a vector where this was actually equal to 0, you know that these guys were approaching zero exponentially quickly. But that contradicts the fact that they can only approach zero subexponentially quickly. People want, I can write two equations that make that look at this. Here, let's use that. If G invariant VV is zero, then Gn of VV is less than some constant lambda dn, where lambda is less than 1, but Gn of VV is also greater than or equal to some other constant 1 minus epsilon dn. Or d depends on epsilon, but otherwise this is true. And so if you pick epsilon small enough, then these two things can't happen at once. I think I've written that correctly, but I haven't gotten it right, so I believe that's the argument for, how do you make the argument yourself? Compute how small epsilon is, so these things can't happen at the same time. I'm going to stop there.
Why is the last line called?
Just because this is right, G0 of sine un, V sine un V. And this is an average of vectors, but if I look at each vector and the average, because I have, there's something I'm hiding in my definitions, right? If my derivative grows subexponentially, you think of that as the norms can't get too big. But because I'm also assuming that on their inverses, it also means the norms can't get too small. And that's really what I'm looking at here. So, when I look at these translates of V, which this is an average of, their size, each translate is not too small, because my derivative is not growing too quickly, which, the norm of my derivative isn't growing too quickly, so the conorm isn't growing too quickly, which means the derivative applied to any vector can't shrink too quickly. This is actually why, if you read dynamics papers, they always define some norm on the derivative that's the max of the norm and the conorm. It's because they always want to control for things like this. And they don't think in terms of group actions, so it's not controlled implicitly in the definitions.
Wait, this acts on the tangent space.
It is true that in writing this simply, right, I really am using the fact that because of the Sobolev embedding theorem, all my estimates that are originally about, derivatives in L2 or vectors in L2, they all become uniform. And that makes it, you could write down this argument without doing that, but it would become much messier because you'd be learning to, well, when I look at pi mu n of v, that's happening at some other point, and it might have done something weird, and, it really matters to make it a short argument that you're doing this when you have uniform control of norms and not just L2 control of norms. You can write it down with just L2 control of norms too, it becomes a mess.
Can you say more about Lafforgue's theorem for non-compact lattices?
I can. Okay, let me approach this by iteration. So how do you prove a property like this for lattices? What does Lafforgue do? Lafforgue proves it for the Lie groups, right? And then how do you prove it for the lattices? Well, you induce, because that's the only thing you can do, right? You look at the representation of the lattice, you induce to a representation of the big group. And now you have this representation with subexponential norm growth. And you induced it to a lattice. And there's a problem if the lattice is not uniform. If the induction to the lattice involves this, Alex Furman was trying for a while to rename this the Margulis cocycle, which is really what it should be named. You have this Margulis cocycle that tells you when I'm at a point in G mod gamma, which element of this alpha gamma acts alpha gx x is n minus after this is a fundamental domain. And when I induce my representation, I'm looking at, say, L2 maps from L2 from G mod gamma to my original Hilbert space on which gamma was acting, and I'm acting via this cocycle by G on this Hilbert space. And the point is, if my lattice isn't co-compact, alpha of gx, you expect it to be roughly the same size as norm G plus norm x. So when x is, even if G is small, when x is very big, the cocycle is very big. And then you think about what happens when I take some vector in this Hilbert space that's supported way out towards infinity. The entire support of the vector is on some small set way out in the cusp. Well, then when I apply my cocycle, I only get huge elements of gamma, which when I apply them, which no longer, I get a huge element of gamma, so even though gamma norm was growing subexponentially, the norm on this vector is going to be huge, even if I take a small element of G. So this is the problem with doing induction. If this problem didn't exist, there'd be no problem. You would just copy Lafforgue's proof in the co-compact case. This is the problem. And there are two approaches you can take to this. This representation of G on here, it exists. There is a representation. This is a representation by unbounded operators. And the first thing you can try to do, which is what we were trying to do, and which I think about 90% of the way works, but may not work in the last 10% because I never got there, is you're saying, okay, it's representation by unbounded operators, but when Lafforgue is doing his argument, he only cares about certain vectors, and operators apply to those. And you can say, well, it's a representation by unbounded operators, but I can still work with it because as long as I can guarantee myself as I work with it that the vectors I have to care about stay away from the place where the operator is unbounded. And you can trace through most of Lafforgue's proof for the G representations and say, oh, that's pretty okay. That's not so bad. Delisle had a much cleverer idea, which is, well, this is unbounded as an operator on L2 of G. My gamma with values in H, but his clever idea was, well, if you are willing to give up some regularity, so if you're, let's say instead of 2, because you have to give up, how much regularity you have to give up, I can never remember. So say you're an LP of G mod gamma with values in H. Well, maybe it's not bounded into LP, but maybe it's bounded into LQ where Q is smaller than P. And it turns out that it is, and using properties of fundamental domains for G mod gamma, you can prove that it is, that it gives you a family of bounded operators from some LP space into some LQ space, and even more, you can iterate this, and go into LS space, as long as you're sort of, in my mind, you're losing regularity. As long as you do this, you have bounded operators. And then you can trace through the proof and see that this is enough to make the proof work. And it is true that, I think we could have written down a proof just using unbounded operators, but there's some parts of it that would get very tricky. Once you have this insight of the tiles, the whole proof is just copying the proof. It's really, you prove this, and then you're careful in your reading of the proof and realize that this is okay. And in fact, I write down a chain of 2 here because you never need a chain of more than 2. You might think, oh, I'm applying large words in gamma, I might have to do this many, many times. Turns out if you're careful in your reading of the proof, you need chains of length 2. And so, it turns out, and showing that these operators are bounded in this sense, there's a standard fact about that this cocycle lives in L1 that everyone knows. You need something a little sharper than that. You need some sharper properties of fundamental domains than that. If you want to know more, I can tell you. Yes.
At this point, you said that for every group satisfying this Lafforgue property acting on a manifold, there exists a Riemann metric.
If I have subexponential growth of derivatives, right? I have to start with this subexponential growth of derivatives, which is a very unnatural thing to have.
Okay, but say for instance, for SL3Z, acting on T3, you have such metrics.
Well, I mean, for SL3Z, for the natural action of SL3Z on T3, my derivatives grow exponentially. They don't grow subexponentially. So, you know, I mean, and it's obvious that the derivative is just the, you know, is just, the norm of the derivative, you know, it's the linear action, so the norm of the derivative is the norm of the matrix. And that's growing exponentially, that's not growing slower than epsilon times than any exponential rate, it's growing at some fixed exponential rate. And so, you know, this is really, you know, this is a very strong assumption that your derivative grows up exponentially.
Last time we did this one.
I think so, yes.
So we should thank the organizers of this seminar, because it is the last one.